So, hello everyone. We're happy to have Vivek Chakrabhavi from the University of Pennsylvania as our first speaker. He will be talking about generalized symmetries of non-supersymmetric string backgrounds. So please feel free to ask any questions during the talk or at the end. We will also leave the discussion open at the end of the talk. Vivek, you have 25 minutes. Please go ahead.
All right, let me just start by thanking both the organizers, first for organizing this seminar series and also for giving me the chance to speak today. So today what I'll be talking about is certain types of symmetries that we find when engineering interesting 4D quantum field theories via string theory. And in particular, I'll try to explore some non-supersymmetric examples today. So what I'll have to say today will be based on a couple of papers. The first of which came out last April, along with a PhD student at Penn, Noah Brager, my advisor, Jonathan Heckman, as well as a postdoc that was previously at Penn and is now at Uppsala, Max Hubner. And there's also a follow-up paper that should be out in very soon now, along with the same set of authors. Okay, so let me just begin by laying out my goals for today's talk. And what I want to do is to engineer interesting 4D quantum field theories using the extra dimensions of string theory. And for the most part, I'll stick to the type 2a setting today. And the way to engineer these theories is to take the extra dimensions of string theory to be a non-compact orbifold singularity. So in the supersymmetric case, the orbifolding group is some finite subgroup of SU3, whereas in the non-supersymmetric case, which we'll try to explore now, it's a more general subgroup of U3. And today's talk will really focus on the set of extended operators, or in particular, line operators that we find in these theories, as well as the symmetries that these operators are charged under. So the plan for the rest of this talk will be to first just give a lightning quick review on generalized symmetries, as well as how to engineer these 4D theories. And we'll do both the SUSY and non-SUSY cases. We'll talk about how to engineer the line operators using branes. And we'll compute the higher form symmetries that these operators are charged under. And again, we'll do both SUSY and non-SUSY. And we'll compute these higher form symmetries in two different ways. One, which I'm calling the geometric approach, which will become more clear as we go. And what we'll do is we'll cross-check this geometric result via studying the quiver gauge theory that we get by taking a D0 brane probe of the singularity. And finally, we'll have some brief conclusions and talk about some interesting future directions. Okay, so what do I mean by generalized symmetries? One thing that the generalized symmetries framework does for us is it presents a global symmetry in a more topological manner. To see what I mean by this, let's consider a d-dimensional quantum field theory and a local operator, O of x, in this quantum field theory. And what I can do is pass this local operator through a unitary symmetry operator, which has support on a codimension 1 surface. And as I do this, I get a linking between the two operators. And this linking is exactly what's giving me a notion of acting with the symmetry on the local operator. So this is kind of the textbook definition of a zero form symmetry. Now, the first generalization I can make from this is to stop considering local operators and instead consider a line operator, which I'm labeling by W. But once again, I'm just computing the linking between this line operator and some sort of symmetry operator. This time, the symmetry operator has support on a codimension 2 surface. And the thing to note here that there's always two different objects that I need to talk about. One is the symmetry operator, and one is the operator I want to charge with the symmetry, or the defect of the theory. So what we just saw was an example of what's known as a higher form symmetry. But there are even more generalizations. So you might have a case where the 0 form and 1 form symmetries have some non-trivial mixing. And this entwinement is captured by what's called a higher group symmetry. Or you might ask what happens if you bring two of these topological operators together. Do they satisfy something like a group composition law? And as it turns out, in general, they don't. and this is captured by what's called a non-invertible symmetry. So let me just say here that I've just listed a few reviews. There's a huge amount of literature on this, these kinds of generalizations now, but yeah. Okay, so those are symmetries, but how do I construct a 4D theory that may have these kinds of symmetries? Um, in particular, what I want to do is engineer four-dimensional quantum field theories using type 2A string theory by organizing the extra dimensions of string theory into a orbifold, where the orbifolding group is a finite subgroup of SU3. Now, in such a setup, the quantum field theory degrees of freedom are localized to the singularity, or the tip of the cone. And I can start to construct the states of the 4D quantum field theory by studying the resolved space of the orbifold singularity. So in general, as I do the resolution, I'll have collapsing 2 cycles and collapsing 4 cycles upon which I can wrap branes. In particular, in this setting, I'll have collapsing 2 cycles upon which I'll wrap D2 branes, and I'll have collapsing 4 cycles upon which I'll wrap the dual D4 branes, and this is exactly what I'll engineer states. So that was the supersymmetric setting. What happens when I remove the supersymmetry? Well, now the only difference is that the orbifolding group is some more general subgroup of U3. However, everything else is pretty much analogous, right? So the QFT is still at the tip of the cone. The states of the theory are constructed in the same way. I still have D2s and D4s, wrapping collapsing 2 and 4 cycles. However, there is one additional subtlety. Due to the lack of supersymmetry, there is a tachyon in at least one of the twisted sectors. And this is creating an instability in my geometry. In particular, the tachyon is going through a process called tachyon condensation, and it's slowly resolving my geometry. We'll revisit this issue of the instability later on in the talk, but for now, just know that it is there. Okay, so that's how to engineer the quantum field theory. How do I engineer the extended, or in particular, we'll look at line operators today. Well, I can once again resort to brane engineering, but this time I want to study certain types of non-compact cycles. So these are cycles that extend from the tip of the cone out to the boundary space. And by wrapping branes on these non-compact cycles, I can engineer extended operators, like this one in blue, that extend from the tip of the cone out to the boundary. And I can restore a notion of linking on the boundary space by wrapping branes on cycles on the boundary space. So once again, there's always 2 things to talk about. There's the defect or extended operator, and then there's the symmetry operator. But for the rest of this talk, I'll really only focus on the defects of the theory. There is one more additional subtlety, which is that some of these defects might get screened. What do I mean by that? So we can construct a whole bunch of candidate defects by taking p-dimensional branes and wrapping them on relative cycles. However, there may also be dynamical states, which you get by taking a p-dimensional brane and wrapping them on certain compact cycles. Now, if these dynamical states terminate on the defect, then those candidate defects get screened away. So what's left over after this sort of screening process is given by taking all the candidate defects and modding out by the defects that have dynamical states on them or ending on them. And that's what's called the defect group of the theory. So at the end of the day, we see that all we're really computing is singular homology groups of the boundary space of the orbifold. And this is encompassing what I'm calling the geometric approach to computing the defect group. What we want to do now is compare this result to what's seen by the quiver. And as a spoiler, what we'll find is that when we study supersymmetric examples, this singular homology approach is good enough to capture all the torsional data. However, as soon as I start studying some more nasty non-supersymmetric examples, I need a little bit more heavy machinery. And so let me just introduce that to you now. And that machinery takes the form of orbifold homology, defined by Wei-Ming Chen and Youngbin Ron in the year 2000. So again, let's consider the orbifold R6 mod gamma, where gamma is a cyclic group. And what Chen and Ron tell us to do is to consider the subset of elements that generate some subset fixed point locus on the boundary space. I'm labeling this by y of gamma. Then the orbifold homology group is given by a sum over all of these fixed point contributions. One thing to note is that we'll always get a contribution from the identity element. The identity element will always fix the full S5 boundary. And so part of orbifold homology is the singular homology contributions. Physically, the way to think about this is that orbifold homology is doing a careful job of geometrizing all of the twisted sector contributions. And we can define a defect group in a very similar way. I'm just replacing the singular homology groups with orbifold homology groups. So now we have two different geometric approaches to computing the defect group. And what we'll do is we'll compare both of them with the quiver result in a variety of examples. So let's just start with a very simple supersymmetric case. I'm taking the orbifolding group to be the cyclic group Z3, where the Z3 acts with weight 1 on each of the coordinates of the C3. In particular, what I mean by this is, let's say the directions of the C3 are given by X, Y, and Z. Then the Z3 group acts via a phase on each of these coordinates, and the weight of the phase is 1 in this case. And let's now take a look at what are the candidate defects I can construct. Well, there are two different types of line operators I can consider. One is given by a D-brane wrapping a non-compact 2-cycle, and the other is given by the dual D4-brane wrapping a non-compact 4-cycle. And what does homology and orbifold homology have to say about the higher form symmetries? Let me repeat. The D2-brane is wrapping a non-compact 2-cycle, so this is taking values in H1 of the boundary space, and it's giving me a Z3 group. I'm labeling this by A1 electric because the object that's charged is actually the Wilson line. And the dual D4-brane wrapping a non-compact 4-cycle is taking values in H3. It's, again, the group Z3, and the charge object is the 2 line. And what about orbifold homology? So to compute the orbifold homology groups, I have to tell you about which elements of the Z3 are fixing some space on the boundary. In this case, it's only the identity element fixing the full S5 boundary. And so what we see is that in this example, orbifold homology is simply reducing down into ordinary singular homology. Okay, and we can try to check this via the quiver. In particular, we'll have a D0 brane probing the singularity and extracting the states of the QFT. In particular, the D0 brane, as it probes the singularity, specifies some basis of fractional branes with open strings connecting them. And this data can be captured by what's called the Dirac pairing of electric and magnetic states. And it's been shown that this Dirac pairing is exactly what's encoding the same symmetry data. The way to see this is to take two of the line operators we're interested in and start winding them around each other. Once you do that, what you notice is that you pick up a phase, and this phase is exactly what's being encoded in the Dirac pairing. Then the symmetry data is encoded into this formula, the torsional part of the co-kernel of the Dirac pairing. So let's break down this formula. The co-kernel is just taking place of the screening process that we saw in the geometric approach. And then the torsional part of that is just giving me back these A1 electric and A1 magnetic symmetries. So let's try to apply this to our example. The D0 brane probe, again, it's going to specify some basis of fractional branes, and I can capture what's called the adjacency matrix or graph of the quiver. It's just the number of arrows going between these nodes. And the Dirac pairing is given by the anti-symmetrized adjacency matrix. That's given at the bottom of this page here. I'm doing one more computation here, which is called a Smith normal form. This is just a mathematical tool. It's not really doing anything, except it is showing that, in fact, we're getting back these two torsional Z3 factors that we saw via both singular and orbifold homology. So in the supersymmetric example, everything seems to agree, both geometric approaches and the quiver. What about if I look at now a more nasty non-supersymmetric example? In particular, I'm picking this kind of crazy example of a Z9 with weights 8, 6, and 3. And the reason why is, one, because it's non-supersymmetric, and also two, because there are additional fixed points in this example. And so you might expect orbifold homology to get additional contributions that singular homology does not see. But let's try to set up the problem by first looking at the quiver and seeing which one agrees with the geometry. And in particular, we already notice a problem when we take a D-brane probe because of the lack of supersymmetry. And in particular, the fermionic degrees of freedom and the bosonic degrees of freedom don't match. And so I get two different quivers, one associated with the fermions, one associated with the bosons. So two different quivers means two different adjacency matrices, which means two different Dirac pairings. And so immediately we need to figure out which one to use, or should I use a composition of the two? And to answer this question, we should recall that the Dirac pairing is really encoding these phases when you wind two of these objects around each other. And we can do that with the whirl lines of two of these particles. And under a 2-pi revolution, what we see is that the chiral fermions pick up a phase, while the bosons do not. And so this is a strong indication that the symmetry data is encoded into the Dirac pairing associated with the fermions and not the bosons. So let's set everything up. So I have the same formula for the quiver, the torsional part of the co-kernel of now the fermionic Dirac pairing. This spits back for me 4 factors of Z3. And we can try to match this with both of the geometric approaches and see what happens. So singular homology, once again, there's a D-brane wrapping a non-compact 2-cycle, takes values in H1, and it's giving me back a factor of Z3. That looks good. That's starting to match with parts of the quiver answer. But we already noticed an issue with the D4-brane wrapping the non-compact 4-cycle, which takes values in H3, and it's spitting back a Z9. Now, this is not as big a problem as it seems like, and it's resolved by noticing that there's like a 2-group-like structure in this case, which if we recall, is when there are some non-trivial entwinement between 0 and 1 form symmetries, and this will break the Z9 down to a Z3. But the more pressing issue is that singular homology is simply missing some of the torsional factors that the quiver is seeing. So let's see if orbifold homology can do a better job. So once again, to specify the orbifold homology groups, I need to tell you something about all the group elements that generate some sort of fixed points on the boundary space. The identity element is, again, generating the full S5 boundary, but there are 2 additional elements, gamma 3 and gamma 6, that generate an S3 within the S5. And we see that by taking these extra contributions into account, we regain the 2 Z3 factors that singular homology seem to be missing. And let me just state again that this Z9 is not a problem due to the presence of this two-group-like structure. So the upshot of all of this is that when computing these defect groups, in the supersymmetric cases, singular homology always does a good job of capturing the torsional data. However, if I go to non-supersymmetric examples that have some fixed points on the boundary, I really need this more robust tool of orbifold homology to get a match with the quiver. All right, with that being said, let's now revisit this issue of the instability in the theory. In particular, there's this process of tachyon condensation. To understand this, we should recall that the worldsheet of the theory is still given by an n equals 2, 2 sigma model, which means that all of the twisted sector operators are labeled by a U1 R charge. And in particular, the tachyons are the most relevant tachyon will be that with the smallest U1 R charge. This will condense first and slightly resolve my orbifold singularity. Let's say it takes some time, T1, to do that. Then the next most relevant tachyon, or the one with the second smallest R charge, will resolve the singularity a little bit more. And this continues on until there are no tachyons left. So the end configuration is either a supersymmetric space or it's a flat space. And so this is giving us a sort of step function approximation for a time-dependent defect group. Since it is a dynamical process, you might worry that we're not accurately capturing all the dynamical data. And to alleviate this concern, we should look at the timescales of the theory. So tachyon condensation is a stringy effect, and its characteristic length scale is given by Ls, whereas the characteristic length scale of the D0 brane is G string times Ls. So in the weak coupling limit, when G string is very small, the characteristic length scale of the D0 brane is actually much smaller than that of the tachyon. And so the D0 brane can be trusted to accurately probe all of these dynamical effects. So the last thing I wanted to mention was just how all of this looks in the type 2b setting. So the
Vivek,
D0, yeah,
Vivek, sorry for interrupting you. Just to let you know that you have 4 minutes left.
yeah, perfect. Thank you. Yeah, I'm almost done. So that's perfect. So right. So in the type 2b setting, the way to get to that is to note that the D0 brane probe system is thrice T-dual to the D3 brane probe system. In the supersymmetric setting, I'm constructing 4D n equals 1 theories, whereas in the non-supersymmetric cases, I'm just constructing some unstable 4D theory. However, I don't have time scales anymore. I have some scale dependence. So the tachyon instability is interpreted as some sort of RG flow from UV scales to IR scales. And the last thing to note is that I don't have one form symmetries anymore. I now have 0 or 2 form symmetries. Okay, so now let me just briefly conclude everything we saw today. The main thing we saw was how to compute the generalized symmetries of interesting 4D theories that are constructed by a string theory. Excuse me. And we did both the supersymmetric and non-supersymmetric cases. And we computed these symmetries in 2 ways. Geometrically via singular or orbifold homology. And we checked these answers by looking at the quiver. Now, what we found was that in supersymmetric cases, singular homology is perfectly good enough to capture the torsional data in the quiver. However, as soon as we start looking at some non-supersymmetric cases, we saw that we need a better homology theory, and orbifold homology was what did the job. Now, there are a few things that I didn't get the time to talk about today that are in the paper, so let me just quickly shout them out. One is we go into more detail on this two-group-like structure that I mentioned. Additionally, we consider another set of string backgrounds, which are those with discrete torsion, which represent a class of backgrounds that are not purely geometric due to some non-trivial action of the B field. And finally, today, I really only talked about line operators. There are, of course, other kinds of operators, so like just local operators, for example. And these are things that we talk about in the paper. There are some interesting future directions that we might take this. One is we might ask, what is the sim TFT associated to all of these symmetries that we just found? And the other is a little bit on a different track, is it's been shown that the D3 brane probe system engineers some theories that are unstable for both very small tubes coupling constant and for very large tubes coupling constant. But recently it was conjectured that there may be some intermediate value where you regain some stability. So it'd be interesting to see if that is indeed the case and also what that special value of the coupling constant is. So that's what I have to say today. Thank you for your time.
Okay, Vivek, thanks for
Yeah.
the nice talk. Are there any questions? You can also ask questions after the presentations in the discussion if you want. Okay, Saab wants
Sorry,
to ask
I
something.
I do have a question.
Ah,
If Sab had a question
Saab,
before me. Sorry.
Saab has a question.
So yeah, just a brief question. First, thank you for the very nice talk. Um, uh, the question will sound strange, but there's a reason I'm asking it, which is you're doing an orbifold rotation. Could you couple that to a shift in some direction? Would there be any issue with repeating the analysis for a case that actually has no fixed point? So imagine you do some rotation by Z9 or whatever case you want, and then shift in some other direction.
Oops, sorry. So I guess you're referring to this example now?
Yeah, it could be for any of these cases, but particularly the
Yeah.
non-supersymmetric case. I'm actually wondering
Okay.
about. Is that doable, do you think, or?
Well, yeah, I see what you mean. So there, you're saying now there's no fixed points to speak of, but so I would imagine at least the quiver approach should be fine. That's not something we've considered, so I'm not 100% sure. But at least I imagine you can still take a brain probe of the singularity, or is right? So
Yeah, there's a route. Excuse me. There's a route to potentially understanding the frozen singularity case, where I think even the quiver theories are not understood properly. If one could do something like that, but
yeah.
maybe
So
yeah.
sorry. Go ahead.
Yeah, it's something we can talk about offline too
Mhm.
at
Yeah, that
some
would
point.
definitely be interesting. So frozen singularities are something that, we talked about briefly, but we didn't go in that direction. But it'd be definitely interesting to see what happens there.
Okay, thank you.
Nacho, you wanted to ask something?
Yeah, no, it's a very silly question. Thanks, Vivek, for the talk. Where the examples that you have considered are like orbifolds of C3 or R6 that then you resolved. Is this like the lessons that you can learn from this are general? For example, if you consider like quotients of more complicated non-compact spaces, since you are checking what's like the singularity and the resolution should be similar.
Right. So the reason we did non-compact spaces because we wanted to turn off gravity.
Mhm.
Once we go to some compact spaces, gravity comes back into the picture, and so you'd expect some of these symmetries to be, well, you'd expect all of them to be either be gauged or broken in some way. So that'd be definitely interesting to see what happens. But and yeah, there's definitely something to learn there. But yeah.
But for example, I see the point of doing non-compact manifolds, but that
Mhm.
not all the six real directions are unbounded. That you could do, I don't know, like C4, C2, and then like a torus. Would that change much? Or
Well, so you if you do something like that, let's say you just want to take a like an ADE singularity,
Mhm.
um, you can do a very similar analysis, and a lot of this stuff uplifts very, very nicely. So where am I? So homology groups works very similarly, and then these orbifold homology groups. Where did I define? Here we go. So orbifold homology groups. This is a very general thing. Now the boundary is in S3, and so you can start defining very similar things. Yeah, the only reason I didn't tackle those cases was just to engineer some 4D theories in the non-orbifolded directions.
okay, thanks.
Are there any other questions? Okay, then let's thank Vivian again for his very nice talk.